Today, I'm very pleased to introduce two professors, Avner Ash and Rob Gross from Boston College in the math department, who'll be speaking about summing it up from 1 plus 1 to modern number theory. And I think this is a great title, and to me speaks to what I find fascinating about real math, the way that seemingly simple properties of integers, addition, and so on, yields this wonderful, rich complexity. And so here to introduce that, Avner and Rob.
Thank you, Richard. It's a real pleasure to be here, and thank you for organizing this. I'm going to speak for about 10 minutes on try to explain what is number theory, and then Rob is going to give an example, a worked out example of number theory, and then I'm going to talk for 10 more minutes about other stuff. So what is number theory? Probably maybe a lot of you know this already, but it's studying the properties of whole numbers, 1, 2, 3, 4, and so on. And it has a long history. One of the nice things about working in number theory is you feel you're connected to a long intellectual history going back to at least the ancient Greeks and probably other ancient peoples. In Plato's dialogues, there are a lot of number theory, very simple number theory is often used as an example of something you can know for sure. And the example Socrates always gives is the fact that some numbers are even and some are odd. Well, that's pretty simple, but that's like the first basic fact about numbers. They divide up into these two parts. And then people started playing around with numbers. You also get in the ancient world people who are interested in numerology. Like 7 is a sacred number, and 6 is equal to 1 plus 2 plus 3, which are its divisors. And the Pythagoreans especially were interested in number theory from that point of view. But as a real theoretical subject in mathematics, the only really important number theorist in the ancient world was Diophantus, who lived quite a few centuries after Plato. And he invented the study of what we now call Diophantine equations. And I'll give you an example of one of those in a few minutes. Another interesting thing about the history of number theory is that it went to sleep after Diophantus, pretty much. And for centuries, and this has something to do with what I'll be talking about in my second part of my remarks. It went to sleep, and people didn't seem to be very interested in it anymore. And the person who woke it up was Fermat, who was a lawyer in France in the 1600s. And he just got interested in numbers. And a big difference between what he was doing and what the ancients could do is that algebra had been invented by that time. So Fermat could use algebra to study numbers, and he got all kinds of interesting ideas. There were a lot of other people at the time interested, like Descartes. And then the subject picked up and has been an important part of mathematics ever since. When you get to the 20th century, there are all kinds of famous number theorists. One of them was Hardy, the guy who discovered Ramanujan, whom you may have seen the movie about. Hardy was famous for saying that number theory had no applications at all. And he was really glad of that, because it meant his hands would never get dirty, with warfare or anything nasty like that. A kind of very pure vision of what number theory was. But the big change, I was talking about this at lunch, the big change in number theory in the last 40 years or so is that it suddenly got these applications, right, to cryptography and cyber things, cyber security. All right, well, that was the history of number theory. Now so it has to do with whole numbers, and I'm going to give you the example, Fermat's last theorem, of something in number theory. But I wanted to just fill it in a little bit with some personal history of my own. In 1993, there was this one night when I couldn't sleep at all. This is the only time I haven't been able to sleep because of some mathematical reason. I mean, the whole night. And it was the night after the day when I heard that Andrew Wiles had proved Fermat's last theorem. And some of the details of the proof had also been given. And so I just thought about it all night, how these details figured out. It's the most amazing thing that has happened in number theory, probably the most amazing thing in mathematics in the 20th century. You may know the story that it turned out his proof was not quite correct. And it had a gap in it which was later filled in with the help of his student, Richard Taylor. So 2 years later, it became a definite theorem. But since that time, I've been fascinated with the proof, with his proof, and I immediately wanted to be able to explain that proof to non-mathematicians. It's a very complicated, very subtle proof with many, many different parts, but that's the origin, really, of our first book. So Rob and I have written 3 books about this, and this was the first one. And so there are basically 3 ingredients, 3 abstruse ingredients that go into Fermat's last theorem. One of them is Galois representations, whatever they are. And we devoted this book to trying to explain to, literally, I wanted to explain to my 6th grade daughter and other children what a Galois representation is. As it turned out, that was shooting a little, that was a little optimistic. But I think we did explain it to someone who really just didn't know much math but could handle algebra. Anyway, that was the Galois representations. The second big ingredient in the proof of Fermat's last theorem we covered in this book. That's the theory of elliptic curves, which are certain cubic equations. And then in our most recent book, the one we came to talk about, is the third ingredient that was needed, that Andrew needed, which was modular forms. So I'll tell you a little bit more about the contents of those books, but quickly, here's his Fermat's last theorem. And this is an example of a statement in number theory, because it's about ordinary positive whole numbers, 1, 2, 3, 4, 5, and so on. You may know you can have a 3, 4, 5 right triangle. That means 3 squared plus 4 squared equals 5 squared. So 2 squares can add up to a square. Fermat's last theorem says that higher powers can't do that. 2 cubes cannot add up to a cube. 2 fourth powers cannot add up to a fourth power, and so on and so forth. That turned out to be very hard to prove. It's famous because Fermat claimed he could prove it, but no one believes that he really had a proof. He made some kind of mistake, or he was writing a little joke. I don't know what it was. So what we've tried to do in our books, so for each of those 3 topics I mentioned, each of those topics can be rooted in something very elementary. So for example, modular forms is rooted in just infinite series, just infinite sums. And infinite sums, that theory is rooted in finite sums, which is just addition. So what we did in summing it up, we divided the book, all of our books are divided into 3 parts, like Gaul. The first part is meant to be very elementary. Really, your 6th grader, if she's motivated enough, should be able, well, she has to know algebra. But with just high school algebra, you should be able to read that first part. And there we talked about finite sums. And in a couple minutes, Rob is going to give an example of what we talk about in the first part of the book. Then in the second part of the book, we assume that you know calculus. And so if you know calculus, one of the topics in calculus is infinite series and limits. And so then we can go and discuss that topic. And then the third part of the book is about modular forms. And that's quite difficult, but if you're motivated enough, we hope that you can read that part of the book as well. So you could ask, we wanted to know who are our readers after we publish these books, and so we get email. No 6th graders have written to me yet. I did make my daughter read the book, so I know at least one sixth grader. Well, she only read the first part. So our readers, though, turn out to be a few of them are, like high school students, real math whizzes from high school. We get some college students and graduate students. And I would say the majority of people who send us email are STEM professionals, engineers, physicists, chemists, often retired, who have time to read the book. But I think the range of emails shows me that we're sort of reaching the kind of audience that we wanted to get to. So anyway, I think I'll let Rob discuss now just one topic so you can see in great detail what a typical number theory question is and how you might answer it.
Okay, so this is going to get hard, but let's start with something easy. Let's add up 1 plus 2 plus 3 plus 4. Okay. Well, why are we doing this? So there's this old story about Gauss, and I'm actually going to ask if anyone in here wants to tell the story about Gauss rather than me doing it. Does anyone know this story about Gauss? Yeah, why don't you just go over to the microphone since you're right over there and just go through it.
Understanding is that he was given some busy work along with the rest of the class to add up a list of numbers, perhaps 1 to 100. And he had the insight right away that you could add them all to each other. And
okay, what's interesting is that that's one way the story goes. That's what's in Callenger's book, which is a standard textbook. The busy work part, all the stories agree on. If you look in Polya says it was adding up the numbers from 1 to 20. Now, Polya is not a mathematician. Is not a historian. He is a mathematician. And then you look in what's undeniably a work by a historian of math, Eric Temple Bell's Men of Mathematics. And he has this really intricate problem involving adding up 100 numbers, but it's not 1 to 100. It's something way more complicated. The trick will still work, but it's a little hard to pin down the details, and I'm not so sure the whole thing ever happened, given this variation. So let's recapitulate what you just said for the people who aren't familiar with the story. If we're going to add up 1 plus 2 plus 3 plus 4, we can run the numbers in the other order. And now the key observation is to add vertically. So 1 and 4 is 5, 2 and 3 is 5, 3 and 2 is 5, 4 and 1 is 5, S and S is 2S. And now we have this labor-saving device of multiplication because we don't need to add 5 to itself 4 times. We can multiply, and we get that twice the sum is 20, and therefore the sum is 10. Okay, now that works in general. If we're adding up the first n numbers, we can write them from left to right, write them from right to left, add vertically, use multiplication, and divide by 2. That works for a lot of sums. It doesn't work for all sums. So the next problem that one would consider where this method doesn't work is adding up squares rather than just consecutive integers. Square the numbers before adding them up. This problem seems to date back to the Greeks, so it is a natural next step. I need a little notation here. Let's call this S2 because those are squares, and let's call the original sum S1. The same idea doesn't work if you write them from left to right, and write them from right to left, and add. It doesn't work, okay? So that's not going to fly, and I want to show you 2 different methods. The first method is very complicated, but I want to show it to you just because it's a way to make this left to right, right to left method work with a little bit more effort. But this is quite complex, and you'll need to look at it afterwards more carefully to see what's going on. Okay, it's a sort of 2-dimensional version. You could say to yourself, the first method isn't going to work again because left, right, right, left isn't enough. We're dealing with squares. We need 2 dimensions. So 1 squared is 1, 2 squared is 2 plus 2, 3 squared is 3 plus 3 plus 3, and 4 squared is 4 plus 4 plus 4 plus 4. So let's take our sum and make those substitutions going down. Okay, and now the idea is that we've actually turned a 1-dimensional left-right approach into a triangle. There are actually 2 different things you can do that will work. You might be able to make something work about diagonals if you try hard enough, but I'm going to go across instead. And so the first sum is S1. The next one is not quite our sum. It's S1 minus 1 because we're missing the 1. The next line, we're missing the 1 plus 2. And finally, the last line, we're missing 1 plus 2 plus 3. Okay, so now if we add down the right-hand side, we have our desired result, S2, is 4 times S1, that's the first column on the right-hand side, minus a whole lot of other stuff. Okay, so now here's where it gets complicated. We're going to rearrange that whole lot of other stuff using our formula for S1. Okay, those little terms in parentheses in there are all sums of consecutive integers, so we're just going to rearrange them. So here's our formula, and instead of 1, well, that's really the sum of the first integer. That's 1 times 2 over 2, and 1 plus 2 is 2 times 3 over 2. And 1 plus 2 plus 3 is 3 times 4 over 2. We'll factor out the 1/2. We'll do a little bit of rewriting. We have some squares showing up when we do the rewriting. 1 times 2 is 1 squared plus 1, and 2 times 3 is 2 squared plus 2. And eventually, we end up with S1 minus 4 and S2 minus 4 squared in the parentheses, which is really neat. And that's going to work in general, okay? If S1 is the sum of the first n integers and S2 is the sum of the first n squares, that same method ends up giving this very complicated formula here. S2 is n times S1 minus a bunch of other stuff. We know what S1 is. We can do some algebra, and we get our desired answer. So that method can be made to work, but it wasn't really good. It's quite complicated. Let me give you a little homework. So the sum of the first n cubes, we can call S3. Use the same trick, expand out the cubes, do this same idea, and you can eventually, with a lot of work, show that the sum of the first n cubes is n squared times n plus 1 squared over 4. It's not easy. I'll give you a little more homework, which is much more interesting. The sum of the first n integers is n times n plus 1 over 2. So show directly that if you add up the first n integers and square it, you get the sum of the first n cubes. I'm actually going to give you a little bit more of an assignment. Not only do that algebraically, but you should also do that geometrically. What's on the left-hand side is a square. Take that square, make it height 1, turn it into a solid, chop it up, and reassemble it into the cubes on the right-hand side. So you can do that, and it's very enlightening. But here's a more motivated proof, okay? Not going to look that way at first, but eventually it will work out. Let's take this polynomial out of thin air, x cubed over 2 minus x cubed over 3 minus x squared over 2 plus x over 6. This has the wonderful property that if you plug in x plus 1, plug in x into the polynomial and subtract, you get x squared. Okay, there's some algebra there, but your telephone can do the algebra for you, so you can trust me on that. And so plug in first x equals 1, and you get f3 of 2 minus f3 of 1 is 1 squared. Plug in x equals 2, you get the next line. Plug in x equals 3, you get the next line. Keep going all the way down to n, and we get this line over here. Now, the right-hand side is exactly our desired result. The left-hand side looks like it has 2n terms, but all but 2 of them cancel. Notice that the f3 of 2 on the first line cancels with the f3 of 2 on the second line. The f3 of 3 on the second line cancels with the f3 of 3 on the third line. There are only 2 terms left when you add up the left-hand side there, f3 of n plus 1 and f3 of 1. The right-hand side is our s2, which is the thing we care about, and we just expand f3 of n plus 1 minus f3 of 1 and get the desired answer. So this magic polynomial f3 solved the problem for us. This obvious question is, where did this come from? Okay, so this is just about a Bernoulli polynomial. Not quite. I'm going to tell you what a Bernoulli polynomial is. Several different ways, in fact. Okay, the Bernoulli polynomials are polynomials of degree k. There's 1 in each degree. There's a b1, there's a b0, there's a b2. b2 is quadratic, b3 is cubic, b4 is quartic, okay? The first one, b0, is just the constant 1. And then thereafter, we define them by saying each Bernoulli polynomial is just about the integral of the one before it. Not quite. Multiply by a constant first. I'll explain why in a second. And integrate. Now, if you define something by integration, there's this constant of integration that's undetermined. And we're used to picking constants of integration as being 0, but we're not going to do that here. We're going to pick the constant of integration so that this polynomial has the same value at 1 as it does at 0. I'll show you some of these polynomials in a second, but those 3 lines completely determine the Bernoulli polynomials. You start out at 1, integrate after multiplying by a constant. I'll explain why in a second. And pick the constant of integration so that the polynomial has the same value at 0 as it does at 1. Okay? The reason that we're going to multiply by a constant before integrating is to make each polynomial begin with x to the k. If we don't multiply by a constant, we start building up denominators in the first term. So here are some of the polynomials. We start with 1. We multiply and integrate, and we get x. The minus 1/2 is this constant of integration that's picked out so that the next polynomial will have the same values at 0 and at 1. We integrate x minus 1/2, and then make the first term start as x squared rather than x squared over 2. And the next constant of integration is going to be 1/6. Here's one more. Again, integrate the previous line after multiplying by 3 so that you end up with x cubed rather than x cubed over 3. There's no constant of integration here as it happens. And here's one more. Okay, so they're not that hard to find. And they all satisfy, this is the key, if you plug in x plus 1 and plug in x and subtract, you get not x to the k minus 1, but k times x to the k minus 1, and that's good enough. So these are actually the polynomials we're looking for. They're not easy to find, but they're the ones that have this property that if you plug in x plus 1, plug in x and subtract, you get a monomial. And the key point is the monomial then can be added up to give us the powers of integers. Okay, so here's an example. If you plug in x plus 1 and plug in x into the third polynomial, and again, better to let someone who is error-free, like your computer, do the algebra than for you to do the algebra, you end up with 3x squared. And then if you divide by 3, you end up with the polynomial we started with because we want to get an x squared. And that's the magic that lets us add up the first n integers. Okay? And the formula then is b3 of x1 minus b3 of 1 divided by 3. Okay, here's formulas for the sums of the first n kth powers. For k going from 1 to 7, we saw n times n plus 1 over 2, n times n plus 1, 2n plus 1 over 6. I wanted to put this on the screen because it's a great example of something that almost never happens in math. Every single conjecture you can make about this formula, based on these tables, is actually true. Okay? So there's nothing misleading here. Very often there are patterns that are true for the first 10 integers, and then they just go haywire. Here they're not going haywire. The degree goes up by 1 each time. You can see that. Each term is divisible by n times n plus 1. That's always going to be true. In alternating degrees, there's a 2n plus 1. That's always true. After k equals 1, the odd powers, the odd k's all have n squared times n plus 1 squared. There's more stuff that you can't tell from here, but for example, if you graph them, they're all symmetric about minus 1/2, which is kind of neat. And there are even more things if you multiply them out. For example, the coefficient of the next to highest term is always 1/2, which is very mysterious, very nice. So that's actually neat, and you can play with that. You can find this table in lots of places if you want to play with them, and it is fun to make conjectures and prove them in that way. The constant terms are the Bernoulli numbers. Okay, so those constants of integration, which were picked to make the polynomials have the same value at 1 and at 0, are these numbers called Bernoulli numbers. After the first 3, 0, 1, and 2. The ones with odd index are all 0, so I can omit them. And they're very mysterious fractions. Okay? The only pattern that you can directly see is that they alternate in sign. And that is not that hard to prove. Other patterns are pretty hard to prove. Okay? And I feel obligated to show you some gobbledygook because the usual way of defining Bernoulli polynomials and Bernoulli numbers is to write down this formula for the Bernoulli polynomials in terms of these things called binomial coefficients, which I'm not going to explain, and then to say that the Bernoulli numbers satisfy this very mysterious formula at the bottom, which, again, I'm not going to explain, and then that is the way people typically define them. Yes, I'm sorry.
Why did you only have E and K on the
Because these ones I omitted were all 0. Okay, yes, all the odd ones are 0, and a very hard exercise is that people often start by writing down this formula on the bottom of this screen and then saying, okay, start with that definition of the Bernoulli numbers, and now I'm going to prove that all of the odd ones are 0. It's extremely hard to do that. It can be done. If you look in some 100-year-old books, you'll see it that way. There is I have to say, a much more motivated approach to this in our book than even the one I'm giving now. But this was one quick way to get to these very mysterious numbers. They show up in number theory all the time. They were involved in one of the methods of trying to prove Fermat's last theorem, using something called Kummer theory. It wasn't quite successful, but they feature critically. They also show up in calculus in a place where you've never seen them. When you study calculus, if you get to the end of the second semester and you're still paying attention, the teacher tells you it's an infinite series for sine of x. The teacher tells you there's an infinite series for cosine of x. They're pretty nice formulas. The teacher never tells you that there's an infinite series for tangent of x because it's not quite such a nice formula. And in fact, it has the Bernoulli numbers in it. A result of that, along with some knowledge about infinite series, is that you can show that the coefficient in front is actually a positive integer, which is an extremely mysterious fact. The Bernoulli numbers are fractions, but multiply them by this very complicated 4n minus 1 divided by 2n, and you end up with it, and then make the sign positive, you end up with a positive integer. Very strange fact. Bernoulli numbers show up in one more interesting way that I can tell you now. I'm going to make a detour here. Tell you, oh, I'm sorry, go ahead.
For your detour.
Yes.
So it's not at all obvious why there's a connection between these particular polynomials and tangent.
Correct.
Is there a succinct reason for that?
Yes, okay. Sorry, so the question is, it's not obvious why these numbers have any relationship to tangent. Is there a succinct reason? The answer is yes, the numbers actually can be related to e to the x, and that's actually the approach we take in the book. E to the x, if you substitute a theta, I theta for x, can be related to sines and cosines. And then there actually are some complicated trigonometric identities to get tangent into the picture, which is where those 4 to the n's come from. So that wasn't succinct, but I hope it gave you a little bit of idea what's going on.
This is the question back to, okay, so why e to the x?
That is actually a good question. That actually turns out to be the best way to define the Bernoulli numbers. And so that's the approach we take in the book. They come from the infinite expansion of the function x over e to the x minus 1. That's actually the easiest way to work with them. Start there and deduce all of the properties.
But you're still not answering his question.
Okay, why e to the x? Go ahead.
This way,
okay.
that if you do what he just said about e to the x over x, or whatever it is, you'll get the Taylor coefficients there will satisfy certain recursion relations that turn out to be identical to the recursion relations we wanted at the beginning to solve our problem about sums of kth powers. So maybe it's like you could call it a coincidence, but that's why it happens.
Yeah. Okay. It is extremely beautiful and extremely mysterious. It is what I would say, and it's nowhere near as mysterious as the next connection, which I'll tell you about now. So, back about the time that Bernoulli was doing that other work, there was a famous unsolved problem which appears to have the name the Basel problem. It's to add up the numbers 1 plus a quarter plus a ninth plus 1/16 forever, an infinite sum. This is the second part of our book. The question is, what is it? Okay, well, it's 1.6449. Okay, ... That's not a satisfactory answer. It is pi squared over 6. Let me give you a little bit of background here. I'm not going to show you that. This is rather hard to prove. It again involves, in one approach, trigonometric identities, which is where the Bernoulli numbers are going to come in. It can be derived using Fourier series, which again have trigonometry in them. So that's one approach. There's an approach involving identities involving cotangent and cosecant, which again involves trigonometry. I don't think there's a trigonometric free way to derive this formula. So a little bit of notation. We're going to call zeta of k, that's that strange letter over there, the sum of the reciprocal of the kth powers. Zeta of 2 is our subject of interest. Zeta of 3 is 1 plus 1 over 2 cubed, and so on. And zeta of 4 is 1 plus 1 over 2 to the 4th, and so on. So Euler showed that zeta of 2 is pi squared over 6. He solved the Basel problem. He also essentially had an identity that let him keep going. Once he had zeta of 2, there's a kind of complicated formula that relates zeta of 4 to zeta of 2, and zeta of 6 to zeta of 4, and zeta of 2, and so on. So you can actually keep going. And he worked out that zeta of 4 is pi to the 4th over 90. Using the identity again, he worked out that zeta of 6 is pi to the 6th over 945. This wasn't part of the Basel problem. Euler seems to have been having fun. Okay, and he got all the way to zeta of 12. Okay, they're all even powers of pi divided by something. And this is an amazing story that not many people know. He got to zeta of 12. He said, 691 is in the numerator. I know where else a 691 shows up. It's the 12th Bernoulli number numerator. This is absolutely true and a phenomenal bit of insight. Euler said, I can prove a formula that relates the even values of the zeta function to the Bernoulli numbers. So what's going on here is we started by trying to add up squares and then cubes. Then we went to infinite sums of reciprocals of squares and cubes, and the Bernoulli numbers show up in both places. There's no good reason for that. So then the next question to ask is zeta of odd numbers. And here, the answer is more complicated. No one knows about zeta of 3 or zeta of 5. Very little is known. Certainly not that it's pi cubed times something or pi to the 5th over something. You have to answer a different question to get increasing powers of pi. You have to add odd numbers, not all numbers. And sometimes you have to take alternating sums rather than all plus signs. And then you can get a formula involving increasing powers of pi. So with that, I'm going to catch my breath, and I'll go back and let you chat a bit further.
So as a non-mathematician, I have to ask you, is it weird that you ask these questions about a series of things that have integers in them, and the answer has a transcendental number on one side and an integer on the other, and it's a weirdly arbitrary-looking integer? Is that as weird as it seems?
Yes.
Yes, yes. That's exactly what I was going to say, is that what Rob's little demonstration here shows is that if you start off with the whole numbers and you're just interested in the whole numbers, it doesn't matter. You're forced to move on. If you want to understand whole numbers, well, first you have to understand fractions. And then we see transcendental numbers starting to pop up. We see calculus. We need to use calculus. And this is what Richard said in his introduction. You start with the simplest objects, the whole numbers, and if you want to understand them as best you can, the subject just grows and grows, and it moves you upwards so that you're learning about more different kinds of numbers. And then you get to complex numbers, square root of -1. That's really important if you want to go further in number theory. So that's one of the beautiful things about the subject. Probably one of the reasons, again, why the ancient Greeks couldn't get very far with it, because their concept of number was too much tied down to commensurability. But in modern times, we have this amazing growth of the subject. And it just keeps growing and getting weirder and weirder, and more mysteries are popping up. And every so often, we prove something. Andrew Wiles proved something, and that gets a little bit... So now we know Fermat's last theorem is true, but that opened up a whole bunch of other mysteries about Galois representations and modular forms. So the question I wanted to raise now is why would anyone be interested in whole numbers or in any of this? And I want to talk about that a little bit, and then we're hoping to have a question and answer discussion, and I'm really interested to hear from you in the audience if you have any ideas about this. But as we were writing our books and thinking about our audience and meeting our friends, and the friends say, what are you working on? I'm working on this number theory. And you know, there's a certain small percentage, maybe 5–10% of your friends who say, oh, that's really interesting. And you sit down, you know, and they'll listen to an hour. You can talk for an hour about this stuff, and they get into it. And the other 90% say, oh, that's interesting. You know, their eyes glaze over. I'm sure that those of you who are in technical fields have had similar experiences. So one question I have is, why does the population divide up like that? For one thing, where does curiosity about whole numbers come from? And that, I don't know. But for myself, I remember being interested from my earliest memories. I mean, like when I was 6 years old, I learned about casting out nines. And then I would just write down lists of numbers and add them up and then cast out the nines and see that it worked out. That was like a great mystery. And when I was a bit older, I learned some algebra, and I just liked solving simultaneous equations in two unknowns, linear equations, and plugging in the answers and seeing that it worked out. Is that, I don't know, is that my brain wired that way? My father was a physicist. Maybe it has something to do with his tutelage. So I was going to ask you, how far back were you interested in math and number theory?
A long way. And I actually remember working out some of those formulas in that table way before there was an internet, and I actually was told that if you add up the fifth powers of the numbers from 1 to n, you get a polynomial. And I remember working this out by hand and checking the answer, and it was great.
Yeah, so this doesn't really give us any insight into why we were interested, why we became mathematicians. And then the other side of the question is, why are so many people not interested? And that seems to be at least partly a cultural thing, because we were discussing this also before the lecture, that in other countries like Russia and France, many more of the general public, at least they have some interest in mathematics. Mathematicians can be rock stars. There's a French mathematician who's like a rock star over there. And there's just much more attention paid to mathematics in some other countries. But I don't think that's really the whole answer. Is it that there's something in American culture that is designed to turn students off? Could it be that all sixth graders, if they were just allowed to play around with numbers by themselves, or most of them, would be interested, but there's something in they're getting some kind of message that it's either nerdy to be interested in mathematics, and then the girls, it's not, you know, if you're a girl, you shouldn't do it, and then you should be doing sports instead. I really don't know. But it's important, if you're writing books for the general public about mathematics, you want them to be interested in it. And in the preface to our book, you know, I thought a lot about, when we were writing this preface, how do we hook a reader? Of course, I don't know what they're doing in the science section anyway of their bookstore or of Amazon, but they look it up, you know, and they look at the preface, and what are we going to say to grab them? And we never figured out a good answer to that. Basically, it says, if you are interested, if you are curious about the properties of numbers, then this is a book for you. You know, and we'll go back as early as you want. We'll start off with the most elementary concepts that you might want. Addition is about as elementary as you can be, and we can build up from there. But what gets a person interested at the beginning, I don't really know. And I'm very curious about that. So the other thing, so there's one other possibility. I mean, as we saw from Rob's talk, and you all know this anyway from any mathematics that you may have studied in school or in college or whenever, it starts off slowly and then it builds. So it's always building on itself. And if you can't kind of retain several different layers, you get lost. Students get lost, you know. And it's not like a literature course where first you read this novel and then you read that novel and then you read that novel. If you didn't understand Moby Dick, you can still understand Northanger Abbey or something like that. But in mathematics, there's much more of this process of layering, and I think that might be why a lot of people drop out of the game at some point. But I still don't understand from early on why more people aren't interested in this really wonderful subject that we've devoted our lives to. So that's, I think, all I wanted to say. Anything to add?
No, I'd want to hear what they have to say.
Yeah, we'd really like to hear any questions or comments that you might have.
Yeah, well, thank you very much.
Yeah, actually, while we're talking about this subject, my daughter is actually homeschooled, so it's kind of a different experience. But it's still kind of curious because we use this program called IXL or something or other like that. And it's very interesting in what they try to do because they're trying to teach kids mathematics, but they're doing it incredibly computationally. And my daughter got pretty good. She's 9th or 10th grade in high school equivalent right now. And she got pretty good at calculating. And she was like really impressed that she could calculate 10-digit numbers. And I, at some point, revealed to her, like, well, that's great calculation, but has really very little to do with mathematics. And then it turns out she got interested in chemistry on her own, more or less. And it's interesting because I can see with the chemistry, I can talk to her about the things about patterns, how acids and bases, and notice how the numbers on this side have to be the numbers on that side. And guess what? That's just equality. That's the mathematical concept. And when she sees that stuff, it's very interesting to her. Now, the part with getting her to do the actual work to solve the hard problems, that's a little more challenging. But there is the interesting stuff that a lot of stuff I think that gets taught these days is computation, because computation is easy. You can easily measure it. You can say, oh, did you get the right number? It's like, well, yeah, okay, you got the right number. But that doesn't give you much clue as to whether they got any insight from getting that number, which is a much harder problem. And I think that's where the problem is. It's not so much that we have bad teachers per se, it's that getting people to get concepts is actually a very challenging thing and a very, very hard thing to measure. And so you've given, as you said, your teachers with the lowest, your students with the lowest GPAs, the hardest problem. How do you measure how someone else is going to succeed? Anyway, so just another.
I actually had a technical question for you.
Yes, please.
So the zeta functions, because they involve greater and greater exponents, does that lead to faster converging numerical estimations for pi?
It would, except the power of pi is higher each time, and it turns out to pretty much average out.
Really? Because they have fast square root algorithms, for example. So.
Right, but the error seems to go, if you compute zeta of 100 and relate that to pi to the 100 and then take the 100th root, it's not the right way to compute pi. There is a lot of number theory involved in the right ways to compute pi, but the zeta function turns out not to be a good way. It's very disappointing because you'd only need to add 1 or 2 terms.
But there's an interesting, a separate issue there that you raise. And I'm not an expert on this, so I might say something that's incorrect. Maybe you can. But so as Rob showed you, zeta of even numbers, so those are the reciprocals of squares, 4th powers, 6th powers, that infinite sum is known. It's a power of pi divided times a rational number. It's easy. And then zeta of the odd numbers is pretty much unknown.
Completely.
Zeta of 3, zeta of 5. Except there's one thing that's known, that zeta of 3 is irrational. It's not a fraction. Right? That's the only one, right?
It's possible
Maybe
that
zeta of 5 is known also.
Yeah, I'm not sure, but very little is known. And it's not hard to go back to your office and get zeta of 3 computed to 100 places, divide by pi cubed, and hope to spot something. We've all done it, and it's not anything. But maybe it's not pi cubed. Maybe it's pi to the 3/2. I mean, you could play all afternoon and see.
Anyway, what I was going to say, though, is if I remember right, the way you proved, this guy Appert proved that zeta of 3 is irrational does have to do with the rate of convergence of a series.
Yes.
So it's known that if a series converges really, really rapidly, then it can't converge, of a certain type, then it cannot converge to a rational number. That's a kind of combination of calculus and number theory. And now the series for the zeta of 3 itself doesn't have that fast convergence property, but the a priori figured out some ways of manipulating it and relating it to some very fast, quickly convergent series. Is that right?
That's entirely correct.
Yeah, and so that's the amazing thing about this subject, is you never know what other part of mathematics is going to come in to be useful in understanding just these properties of these simple whole numbers and fractions.
Regarding the question of how do you interest people in number theory, given that unlike in Hardy's time, there are applications for number theory now, is there a story to tell there where people might be interested in the applications and the number theory is actually possible for lay people to understand?
Yeah, I think so. I mean, I think books have been written about that. And so if you look at the range of books that, of mathematics for sort of the general public, then there are different types. And one type is to concentrate on these applications. And that's one good method. That's something we sort of wanted to avoid in our book, because we wanted to try to put this out as something very pure and theoretical, just because that's how we view it. But there is a good, that's a good way to go. Another way is to talk about the biographies of the mathematicians. That's pretty popular. And then there are quite a few books that are just treat the mathematics itself, but they usually start at a higher level. And what we wanted to do is to bring this down, at least at the beginning of each book, to bring it down to the lowest possible level we could. And the last one, summing it up, is a little bit more difficult, actually, that the algebra gets heavy really fast. If you look at our first book, Fearless Symmetry, that's in a way that's harder to understand because it's more abstract. But in terms of the math that is involved, the whole first 8 chapters involve nothing but addition, subtraction, multiplication, and division. And yet we're studying some very interesting properties of numbers, namely, if you divide one number by a prime number, you get a remainder. We're interested in those remainders and how they fit together. And that's the beginning of the story that leads on to these Galois representations that are important in the proof of Fermat's last theorem.
I think I could provide a little insight about mathematics in Russia, as I'm a college student from Russia. So actually, mathematicians and engineers are not viewed as rock stars in Russia at all, at least in general public. But if you're interested and motivated and you want to attend some elite school and get into STEM field at some point, you have opportunities. There are, at least in the big cities, there are very good and famous schools with great curriculum in math and physics, and like proofs are all over math curriculum. There are also some, if you don't get into a light school, you can probably still attend some math circle starting from middle school, which again exposes you to the number theory, partly to calculus, starting from 5th grade or something. That's how I personally got involved into math field.
Yeah, in fact, down the street from where I live, there's something called the Russian School of Mathematics for I think they're for school children, to give them supplementary education in mathematics. I was just going to say, maybe this now will be obvious. I was going to summarize by saying, why should we get people interested in mathematics? Besides, selling our book, who cares? So just to summarize, but I think you've all probably heard this before. First of all, mathematics is the language of nature. That's what Galileo called it. And
he didn't have group theory in mind.
Well, actually, group theory turns out to be just as much there, but he didn't know. Yeah, well, it was very insightful of him. Yeah, mathematics is the language of nature, and so people who might not be interested in mathematics per se, I mean, most people are interested in some part of the natural world, and if you want to be a good citizen, you need to know your basic mathematics. And there's all these horrible stories in the newspaper about people don't have any financial literacy. They don't understand compound interest. They don't understand global warming, things like that. All those kind of things would be better served if we, and I think maybe as a society we are slowly moving in the direction of making mathematics more accessible and more fun for all people, not just for this 5 or 10% who get born interested. And then finally, we want to have people going into the STEM areas. We need more and more people educated in mathematical sciences and engineering and so on. So you need a bigger pool to draw from. So I think those are all good reasons for writing books like these and trying to get people interested in mathematics.
Well, thank you very much.
Thank you.